No COG shift. And then after preliminary analysis, we have now the weight of the pad I. So we will add weight of the pad I here, at this joint, and at this joint. Okay? So we will add the load under GC key. Load, go to joints, and select the joint you want to add that weight pad I. So select this, press Control, select this, select this, select this. Okay, the pad I location here, 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 and here. Okay, then press Apply. Then under GC key, so that's jacket miscellaneous load. Under GC key, press OK, and then I will define pad I. Okay, and then add, put negative 9.81, so assuming 1 ton, including stiffeners. 9.81, and press OK and save the file. Okay, press OK, and save, because I have already modeled it. Okay, so press OK and then save. Ready? Okay. So after that one, I will add also cone guide, because we hadn't modeled, we haven't modeled the cone guide. So make it bigger. The cone guide is actually in here, so we have the cone guide, so it should be acting downward. So I will select these 3 members here, this member, this member, and this member, to apply cone guide weight, because we haven't modeled the cone guide. So I will go to load, and then it will be members. Okay, member, I will select this member, press Control for a multiple selection, select this member, this one, the other one is this. Okay, and this side, this cone guide here, another here, another here. So you have 6 members to be loaded, all in vertical direction. Press Apply. So in here we have GC key, but it should not be pad I but cone guide, CONGD, cone guide, CONGD. So you can check your work if you do like this, the load ID, and then put concentrated, and then press Add, and then force should be global, so we have to consider global Z, and put minus 3.27 kilonewton. So 3.27 H, so 3.27 times 3, that should be approximately 1 ton. And then distance should be 0.1 meter. Okay, so from the edge, 0.1 meter. Z 3.27, 0.1 meter. Okay, and then press OK and save the file. Okay, just press OK here and then save the file, because I have already modeled this one. Okay, so just press OK and save the file, and then check your work. Go to display, labeling, go to load if it's already defined. This under GC key, right? Press OK and then scroll down. So I have the cone guide, I have the pad I already. I have anode, cone guide, mud mat, and pad I. Okay, so once it's already there, run the analysis to recompute or relocate the location of the COG, because once you update the load or once you update the member section, your COG will change. Now take note, your lifting point should be at the COG. That's the rule when lifting analysis will be performed. Okay, So after this one, you have already checked. Save the module now. And we will perform a rerun, the static analysis. Okay? So this is now the master copy. Run file wizard. It should be in linear static. Start wizard. Scroll down. Scroll down. Select that file. Select that file. Press open. We need post view to check the work. So check post view and join check also. Check perform tabular check. So we have already the join-can input file. Okay? So press OK now. So this is your file. Now at this stage, we don't need SACS common solution file. So you can uncheck this, keep this file. Meaning to say you didn't want to put SACS common solution file. We don't need COC file also at this stage. So press X, and then run the analysis to check the COG, if it will change or not. So check if no errors found. So in this case, no errors found. I will check now. I will go to the load case center. Go to the load case center and check the center of gravity for the gravity load. So in here, okay, we will use this one. Now we will use this one in computing COG shifting. Okay, so I will copy this. You are already at the center report. At the center report, you just go to edit and then go to find and then center. Find and then center. Type center. Meaning to say you want to go to center. Center. Go down. Okay. Find next. Find next. Yeah, this one. This is the location. So we updated. So I will carry this one. Now I will copy this one. Copy. Copy this. Right click. Copy this portion only. And then go to the COG file. This one. Open your COG. I have already sent to you this file, right? I think yesterday or yes, yesterday. So go to here. You can use that one and paste somewhere here. Go to that file first. Copy and go to Excel. This file. I have already sent to you this file. So we will check the COG shifting. Copy. Open the file, the Excel file, and then paste. We can use that one. Right click and then go to paste. So I have already this. But it's not arranged. See, it's not arranged, right? So if it's not arranged, you can convert. This is one method also. You can do like this. From Excel file to SACS file. You can do that. Or from vice versa. You can do like this. After right clicking and then copy. Go to data. Go to data. And then you go to text to columns. So that it will be arranged in vertical. In columns. Okay. So data. Text to columns. Just scroll next. Okay. So the lines, you can check that later on. Next. And then finish. So it's already this. So I have already the gravity. It should be the gravity. You have to consider the gravity loading. So you have to check. I will make this automatic. And then the gravity should be in color red. Okay. So for gravity loading, I have now 3270. The centroid is negative to 8.19 and 0.59. So we will update that. We will update to 8.19 and 0.59. Delete that. Go to data, text to column, delete first. Yeah, right click, copy paste. Okay, do not change, like that. Go to text column, and then next, finish. Yeah, so we're done. So you have already the file. So it is, you can use this one already, na? Yeah, you can use this one. So we need the gravity load. Okay. So the gravity load, I will update this one. I have already put LX is correct. This is manual input, no? The red, the red color are manual input. We need to consider the L average because it's tapered, no? It's not uniform, unlike top side. So we will convert this length and this length into average. So LY1 plus LY3 is the average along length, nah? So LY average. And then LX also, this LX here, distance from here to here. Okay, so everything is actually calculation, in terms of, I have already put what is L and B. B is average. So I need to consider FZ. So I just put FZ, go to gravity load. The gravity load, FZ. So this one. FZ, the gravity load. But you must consider negative sign, positive. So press gravity. And then the location of the center of gravity. Location of the center of gravity. Original is how much? So I have here minus 28. This one on the gravity. Okay, enter. And then on Y, COG Y equal, and then select the Y. So we need to consider Y. Enter. So this is now the location. Now the rest are calculations. So we will check first the base COG. The base COG, the center of gravity is minus 28, 19, and 0.59. So we will check, we will go back to the original base case. Okay? So go to this. Go to this file. This is the original base case. We will update the COG. Go to model. And then check the joint. Lifting joint is 2819. Is that correct? 2819. So it's okay. And YCOG is 0.59. So 2819 and 0.59. If it's not that value, then you check. You change this one. In this case, because I have already checked this one, so that's why I come out with this value. If it's not, you update. Okay, you update, So your Z, copy, you have already copied that one across? Okay. If Z is gravity load. This one, yeah. So you have to update that one, Update the value of X because we add pad I load, we add cone guide load, so your X and Y will change. You have to update that. So that's your final, So in this case, I have 2819, see? So that's correct, right? So 2819 and 0.59. So you update. I think in your model, it's not yet updated. So you have to update that one. Update now. You put minus, to here, put minus. You need plus. Yeah. No, it should be minus. It should be plus. Equal to this value, but you have to consider minus. See? Plus, it should be plus. Downward, automatic downward. Okay? So, update now. Press apply. So, this is 2819. And then, that's now the base no COG shift. No? The base, no COG shifting. Okay. So, you have to check this one. Once you update everything, X, Y will change. Okay? So, this is now the base case. We will copy this file and perform the first COG shift. So, in top side analysis, we didn't specify it further, right? So, in this case, we will do like this. Make a folder and copy that file. Huh? Okay, do not close. We'll make a folder on the jacket folder. I will put COG shift 1. And then I will indicate what type of shifting. So in this case, I will consider the first shifting, which is minus X plus Y. Nah? Shift 1 minus X plus Y. Minus X plus Y. Okay? So this is shift number 1 minus X plus Y. And then copy the SACS file in the base case no COG shift. So go to that file, copy this. Now this is the file now. Copy. And go to COG shift and then paste. So you are now at the SACS COG 1 minus X plus Y. What is the difference between shift 4, shift 1, shift 2, shift 3? The difference is the location of the lifting point. You shift it, okay? So in here, go to the folder, go to model, and we will change the location of your lifting point. So, from here, you see, shift 1, your new COG is 29 and 1.44. It's already calculated, see? Nah? So, these are already embedded. So, formula is already embedded. So, all you have to do is put these red colors, put the red colors, value in the red colors, and automatic, these are your locations. Nah? So it depends on the value of delta Y and delta X, which is 5% LX and 5% LY, but should not be more than 1 meter. So as per our basis of design, okay? So shift 1, the location of COG is 2919 and Y COG is 1.44. This is already the shifted. Nah? This is already the shifted value. Okay? Meaning to say, from the original, this is the original, right? I will move to the left by delta Y or delta X and then up by delta Y. So that's first shifting. That means plus X, minus X plus Y. You see? Minus X, because this is my X-axis, this is my Y-axis. I move minus X and plus Y, so that's shift 1. Okay? So the value of delta X is this. See? 1 meter to the left and 1.85 meter up. So this is now shift 1. Okay? Now the coordinates is 2, 9, 19 and 1.44. So I will follow that one. I will go to joint, modify, and select the hook point. 29 point, how much that? 19? Yes, that's the same. You will change the dummy and the hook. Same. Yes, yes. You have directly beneath that one is the dummy. You will change the hook, you will change the dummy. So in this case, this is dummy. 2919 and 1.44. Okay? 2919 and 1.44. 1.44. Okay? Apply. So, as what you did in dummy, you change also the hook. Where's the hook? Okay, this dummy and the hook. 2919 and 1.44. Okay? So that's the difference. COG2. Oh, move it to COG2 location. COG3. Move it to COG3 location. Move to COG4. So this is 2919 and 1.44. Apply. Okay. Now, when you move your COG, what will happen? Your center of gravity is here. Your COG is here. It will rotate. It will rotate, right? So, to compensate that rotation, you add a couple. So, that's the couple. That's the principle. Say, for example, you didn't perform the COG shifting. You just only shift the COG. What will happen? I will run the analysis. We will run the analysis and we will see what will happen. If we will shift only the COG without applying couple. So I will go to run file wizard, reset. I am now at COG shift minus, run the wizard. Okay, you have to run the wizard. Select the input file. This is SACS. This is now the COG shifted. Open. And post view. We don't need to check joint can at this stage because we didn't apply the COG shift, right? We need only to check the post view, okay? I will uncheck this one. I will uncheck COC file and run the analysis. Okay. Go to post view. Go to post view. We shift the COG location, the hook point, but we didn't apply couple. What will happen? Now the rule is the reaction on the spring should not be more than 10 kilonewtons. Lesser will be good. Okay? So go to display, go to labeling, go to force reaction X. You see it big. Huh? It's 32. Oh. 320 kilonewtons, more than 1 ton. It's impossible. This means that your location hook point is not at the COG. So what will you do? You have to add a couple. So this will now the couple value. So shift 1, I have, you use the total, this one, You use the total value. Shifted X, shifted Y. Okay, this is the principle, I think this is what mentioning. Okay, for example, this is my original, This is my original COG. This is X axis. This is Y. We are looking at the plan. We want to shift the COG minus X. So this is delta X minus and positive Y, right? So delta X actually has a value of 1. And this one is 0.85. So this is now your new hook point. That's the new hook point, right? So, in order to compensate that one, if you shift this to the left, your moment on Y should be to the right. MY. To compensate this one, because it will be rotated in the left. Your weight is already here. So you move that one, so you apply my. If you put your load on that direction, what is the location of your mx? Opposite, always opposite. If you move in that direction, clockwise, it should be here, right? Mx. Moment about x is, this should be the applied moment. Now, if this is the joint, so you see there are joint, right? Huh? These are the joint 219, 299, 199, 199L. Okay? This is only for example. I have here joint 1, joint 2, 3, 4, at which I'm going to put my couples. So I'm going to ask you mx, my, this is the joint. So 1, 2, 3, 4. The formula in computing the force due to x is Fz times mx. So it should be delta y or moment over 2 and then length y or x. And then m due to y, that's the force. Fz delta x over 2ly. It's actually embedded. You have the program already or the formula. So this is now the forces. Equivalent due to bending. Now, if I will ask you mx, moment about x, what will be the force on 1 and 4? I'm talking about 1 and 4. So I'm looking here. It will be like this, right? What is the moment? What is the force? Upward or downward? So I'm looking here. I apply a moment mx, right? So this is what? 2, 3. On that side, 1, 4. Is that correct? So this one is what? Up, down. This. It should be upward. This should be downward. Right? So downward means minus. So that's why you notice that the value is on 1. 1 and 4 is downward. 1 and 4 is downward. So this is minus. Minus. This is plus. Plus. On my also, due to my. Okay? My here is on that direction. Upward is 3 and 4. Right? And downward is 1 and 2. So you have minus, minus, plus, plus. You add this one, that's the total force you are going to apply. Or you will use the formula. I have already the formula. Use that one, it's already correct. So total, these are the total force. You add this one and this one, so you got the force. Okay. We will apply now the couple. Okay. Now, the application of couple is actually, you can put it at the top, you can put it at the bottom. So in this case, I will put it at the top to be consistent with the top side. So I will go to model. I will apply now the COG shift. Couple. So this is joint. So this one is 29. So it's already correct. I will apply the two couples here. Here and here and here and here. Okay. So go to load. Go to load. Go to joints. And select this one. Select the point. This is the point. 219L. 219L. So what is 219L? For 219L it's minus 13.5, right? 219L is minus 13.5. So I will apply and then I will put COG1 as my load condition, and then my load ID is minus X plus Y shift. Minus X plus Y shift. I will put add, and then put, what is the value? Minus 13.5. We will check minus 13.5. So this is 13.5. Okay? So minus 13.5, press OK. So you notice this is downward, minus 13.5. Save. Now, usually the value, if this is downward, automatic, the opposite is downward, upward. Then directly opposite to that. So just let's select 199. Select this, the opposite side. 199. Press apply. Same COG, shift. Same load ID. Add. But this one should be plus 13.5. Or we will check 199, 13.5. See? It's plus. Okay. I will put OK and press save. On the other side also, I will put this. 119L. What is 119L? 119L is minus 126.3. 119L. Apply. Same. Minus 126.3. 126.3 119L. So this is correct. Okay. And then press OK. So this is on the side, downward. Directly opposite to that, it's coupled. So it should be opposite always in direction. Press save. Select this joint. Apply. Same COG. Same load ID. Add. And then change the sign to 126 positive 0.3. Couple, it should be always opposite. Press OK. And then save. Now, this is the checking. Save the model first. Save the model. Your moment created should be equal to this. Should be equal to that. This. 277, 3220. So you can check. Display. Labeling. Go to load. The load case is COG1, right? COG1. Press OK. Check all display all types. Press OK. So 2778, 525, and 3271.2. No FX, no FY, no FZ should be created. It's only bending moment or couple. Because like this, if you move here, your moment should be here. If you move here, your moment should be in that direction. Always opposite to that location of your hook point. Because when your hook point is this and your center of gravity is here, you got twisting. But if you have the location of your hook point here and you apply a moment in here, it will be unstable. Okay? So we will check. After introducing the COG1, of course, we will input this in our load combination, of course. Okay? So go to load. Go to load. Go to combine load conditions. And select. We will update SQ1. SQ1 is gravity, SQ effect, plus the COG shift. I will update SQ1. Press OK. Edit. So see, gravity plus SQ1. That's SQ1, right? SQ1 is gravity plus SQ1. I will add COG. Add. So this one. So already gravity plus SQ plus shifting. Press OK. And then SQ2 also. I will edit SQ2. I will add shifting. So this is now my load combination for SQ2. Gravity, SQ1, COG1. Press OK. So it's already complete. Gravity plus SQ effect plus COG shift. So that's COG shift. No? If you have COG shift 2, you add COG shift 2. Close this and save and perform the analysis. Perform the analysis. Okay, I will close this one. You must check first the model. So go to data file. You can check it in edit file. Once you have already familiarized what is the command, you can check it in edit file in here. You can check it in here. Oh, it's in data file. So check. Okay, this is gap. Change this one to static. Standard. Make it standard. We will discuss later on. Go down. Load combination. So we didn't change. Except SQ1. This is with SQ effect plus COG shift. SQ2 is gravity. SQ1 plus COG shift. So this is correct now. LF1, 2, 3, and 4. That's the case. Okay? So I will perform now the analysis. You can update also this one. The SQ. Because we changed. We have the pad I plus the cone guide, right? You can change also this one. So just update that later on. Okay. Perform now the analysis and check the reaction of springs. It should not be more than 10. The smaller the better. Okay? So I will perform now the analysis with joint can. So you have to reset this one. Reset, okay? Now take note, in the COG shift 1, we don't have the joint can, because the joint can file is in the base case. You can do that also, Start wizard, the SACS input file, all files, select the file. So this is now my file. Open it, and then check post view in order for you to have a post data view. And join check. Perform tubular join check. And then scroll. So we don't have the file. So scroll it down. So you notice if you put join can scroll all files, it doesn't have the file. So you have to select. You have to go to the folder where the join can file is located. Where is it? In the base case, So in this case, I will go to this tab. And then I have already it in the jacket folder. See? The base case, no COG shift, where the file is located. So I have now the join can. So open the file. This case, no COG shift, join can, and press OK. So I have now already. Or simply, you copy the join can from the base case to the COG shift. It's okay also with that. Or you can do, because you have only one join can input. So no need to have multiple inputs. You can select, Okay? So after that one, I will perform now the analysis. Run the analysis. Is everybody following for this joint can? Because I select, you can change this one, You can change like this, For example, I don't want to go to that folder. So what will I do? I have the file in the base case. I will just copy it across. Copy. And put this in the COG1. Right here. Paste. So I have already the copy, right? Okay. Without changing that one, I can change everything. I will go to right. I will right click this one. And then replace. I can replace that one. So in here, jacket COG shift 1. Right click and then replace. So I have already the file. So no problem. You can replace this one. No, right click and then replace. Right click and replace. So I will perform now the analysis. And then I will perform. I will see what is the reaction. Display. Labeling. Force X. I will check. This is the first thing to do. You have to check the reaction. So this is so small now. You notice? 0.2, 0.057, 0.3. When we didn't put the couple, the reaction is 32 kilonewtons. It's quite higher. Na? So, point 309, display, labeling, force along Y. So, it's small. Now, another thing. Sling should not carry compression. Na? Shifting usually will create compression. So, in this case, display, go to display, labeling, member, and then check compression. No compression. So, it's okay. No problem. Na? If you want to view the tension to determine the force on the pad I, or to design the pad I, go to labeling, go to tension. So, these are now the tension. So, in this case, no tension occurs. How about if there will be tension? What will you do? Because you cannot avoid that one. Sling could not carry compression, right? Just like this. Same as this. It will carry only tension, but compression, no? Sling will not carry compression. So what will you do if it will carry compression? You will use gap element. Tension only. No? Gap element actually doesn't need input file. You can model it inside. You can model it outside. The loadout for top side, that's outside. That's why we need input file. If you wanted to make in the model, you can do that. So like this, I will use gap element. This is how to model gap element inside this model file. Okay, I will close this. First, I will go to model. Select sling as tension gap only. So I will go to member, modify. I will select the slings. Control, select the sling, press control for multiple selection. This one. So I have now selected the sling, and then I will scroll down. You see, you have member type. So in the member type, scroll down, I will put tension. If this sling will carry compression, automatically it will be deleted by program. No need to delete. It's automatic, So I need tension. I will put apply. I consider now gap. What else? What you will do? You notice if you go to options, you notice we select this as standard, right? So you have to define it as gap loading. So that's the second step. First, modify the member as tension only. Second, load selection should be gap. So I will go to options. I will go to load condition selection. I will go to gap element. Gap. And then I will check the final load combination. It's LT1, right? Add. LT2, add. LT3, add. LT4, add. Meaning to say, I want LFT1, LFT2, LFT3, LFT4, gap loading. Update. Okay? So that's it. We have already now gap analysis. Close this. And then you have to reset because this is in linear static. It should be in here with gap element. Okay? Linear static with gap element. Start the wizard. Select the file you want to run. So in this case, this is my file. Open it. So see, use gap input file. But we don't have gap input file, right? We don't have gap input file. So just scroll this down and then use gap element options. Because the gap element option earlier, the load selection is gap. So gap element options, scroll down and select use gap element options. I will increase the iteration. Maximum of 9999. So I'll just put like that. 9,999 number of iterations. I will go to post view. I will go to join check. And check perform tubular join check. So it's already there. The gap input file. If you don't have that file, then you can scroll down and select where is that file located. Okay? So we have now the post view. Press OK. But you have to check. You have to go to model. Because in the first, go to this file and then check data file. See? You have two cases. Static, gap. Delete the static now. Because this is already in gap element analysis. Right? So delete this load select in static. Cut. So it should be in gap element. It should be in gap element because you perform gap element. How about if I will not put gap element here? It's useless. It's useless. Okay? So you have to put the load combination in gap. In GP, right? In GP. Okay. It's done already. Run the analysis. Okay. Now go to gap list. In this list, you can check if the member carries compression or not. So in this case, since we have tension, it will be tension all. So go to gap list, double click, scroll down, and then you find this. This is the gap element report. In the gap element report, you can see tension axial. So all forces are tension. All forces and tension. See, it's almost 2.8 in tension. If the case, there will be compression, automatically, this value here is 0. Meaning to say, it's deleted by the program. Okay? You have here, so it's too small. Okay, so all member carries tension. So that's how to use the gap element. Now, if I don't have gap element in my module, what will you do? What will you do? Okay, this is the case. If in case you don't have gap element, on your analysis, you notice, in your static analysis, you notice, for example, this member carries compression. Okay, this one. So, if this carries in compression under linear static analysis, what you will do is to remove this one. This is what designers did. If this member carries compression, without gap element analysis, what they will do is like this. Member, delete that member which carries compression, apply, and then no skew effect. No skew effect, meaning to say, all my loads here will be, or my point should not be on dummy but on hook. Loadings will be changed. No skew effect. It's only COG shape. No skew effect plus gravity only. Why? Why no skew effect? Skew effect will be used only for 4 slings. 3 slings, 2 slings, no skew effect. There is no misalignment on that. 4 only, usually 4. So that's the explanation. Nah. You perform COG shift 2, COG shift 3. In COG shift 3 and 4, there is compression. There is compression. So if that's occur, you have to delete the member or the sling which has compression. You consider only 3. It will run. It will still run. The analysis is still the same. The analysis is still the same. But in reality, compression will be negated. It will be deleted automatically by program if you will use gap element. So that's the procedure. So COG shift 3, 4, and 2, it's homework. It's homework. Is everybody's PC running? Or the analysis running?
I have to check.
Huh?
Có ai chạy chưa? Nào đi.
Well, anyway, the procedure in topside lifting is the same with jacket. Just the same. So we'll go to loadout. Yes, yes. I have already presented. I have already prepared. So it's a complete from our first meeting up to here at this meeting. But it's different. No, it will be on the 80 meters water depth. So the levels high. So from that on, we will use lifting. We will perform lifting. We will perform load out topside, and then load generation, of course. So it's practice. Usually, you will learn SACS not just only 2 days, 1 week. No. Even it took me years to know, not to master, because I'm not master. Above is the master one, but no, I'm not. Just only. So you have to study. You have to study. If you have, do you have the manual? You have the manual, SACS manual? You can go to, in here, manuals. See? Directory, go to manuals. This, in the manual, C state, in C state, double click, see? In C state, there is how to model a jacket, see? You don't have file? No.
I don't.
Your DLL is not connected with the CPDF. It's cracked. Everybody's copy is cracked. It's here. So, see, loading, factoring, allowable, load combinations, it's here. Property overrides, win areas, member weight, not structural weight, it's already, So you can see here. But it really takes time. It really takes time, So practice. Usually in our daily activity, like for example lifting, you know lifting. But other like in place, fatigue, which is the usual case for consultants. No? So how to create environmental loads? You have environmental loading. So you have live load, the type of wave. Type of wave. This is for in place. No? We have in place, we will use this one. We will use the API. The wave type, critical position, something like that. So you have to read. No? So I think on Thursday or either Friday, we will have a quiz. Huh? Yes, quiz, modeling only. It's not actually in the quiz where we are a student, where you don't know it, you will be scolded. No, it's not like that. So we will give you a figure. You have to model the jacket. You have to model the top side. You have to model the skid weight. You have to model everything. Perform the analysis. Load out, lifting. Load out, lifting. Yeah, after. The principle is the same. It's load out, top jacket. It depends on the installation procedure. Like for example, top side. Top side also can be done in skidding. Have you performed skidding top side before? Future, if it's heavy, you cannot lift it. You have to skid. You provide skid shoe. Yes. We have a project in Total Indonesia. It's a legged 8-legged platform. It's the top side is heavy. You cannot lift. You cannot use trailer. It's heavy. Yeah? So what we did is skid shoe. So it by just like skidding, jacket skidding. You put winch, skidded, 2 bars. Uh-huh. Yeah. For heavy lift. Or skidding and then use float over. Jack. But you have the barge movement. It will be bumped on the fender. So you have to analyze the piles. You need the barge stability. What is the force on the fender? And then meeting analysis. You put load. Yes. So we load it up. And then once it's up, it's lowered. Sitting. Build. Done. So float over. No, that's float over. So we still at load out. Maybe we can start load out. Shall we start? We'll just only model, na? Just the same with top side load out. Okay. So after the analysis, na, of course you will make a folder. You will make a folder, name it jacket loadout. Na? Close this one. So SACS loadout I have already here, but this is top side, na. So I will put folder jacket loadout. Usually, the model in lifting will be used in loadout. Yeah? So what you lift will be loaded out. Okay, so I will copy the jacket, jacket lifting analysis. I will consider first the base case no COG shift. I will copy this one and I'll put it in the folder. Loadout. Jacket loadout. So I have now already the file. Go to that folder. Jacket loadout. Go to model. Delete. Delete the hook. Delete joints. Delete this. Delete this pad I here because we have already applied the load. Delete the pad I here. Pad I. Save. Now be careful with this joint. Sometimes this cannot be deleted. So you go to joint, go to springs, select this, apply and delete the 100. Okay. I will need that later on. Just make sure, Okay, we haven't got the basis of design for jacket loadout. So what will you do as a structural engineer? For example, I will not give you that the deflection is 25 or 50 or 30 or 60. The same, different with the top side. So what will you do? So in the absence of specific data, because some client will specify, we need only 25 mm or 50 mm. So it should be like this. In the absence of specific data, for example, this is the jacket support. You will do like this. First, you will analyze without this support. That's loss of support. But you have to consider limitations on the deflection. Like for example, in the Bindung project, I've seen in the Bindung project, the limitation is 100 mm. When this support is lost, the limitation of this maximum deflection should not be more than 100. So you have to check. Okay, so this is the case. You have the jacket. This is your bars. This is your cane. So when it is loaded, some of the support will not carry. This one. So you can simulate also this support will not carry load. So the support only will here and here. So this one, when this case is like this, you can check it in gap, no load. Gap, no load. So when this support is not acting, the maximum support is here, here, and then you have to check this member. Okay? So in the absence of specific data, we will use no load. We will not consider deflection anymore, because we don't have the basis of design for this. So you have to perform no load. Okay? So I will define now the gap. To define gap, you add a joint. No? Because gap element should have a length of not less than 0. You can put 0.5. You can put 0.05. No? So I will add adjoint. I will add adjoint here. I will add a support here. Support, 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 support. 6 support. Now, it is unlikely for a skid beam to be in this direction. It should be horizontal. But for analysis purposes, we will utilize this one. Okay? You understand? Yes. So, skid beam should be like this. Have you seen a skid beam like that? No. It should be like this, horizontal, right? But in our case, it's tapered. So, I will add a gap joint. I will add a joint relative. Relative. Select this joint. I will add a support here, a dummy support. Now you can change this one. S1. Make it S1. And then add minus 0.5. 0.5. Apply. Okay. In here as S2. 0.5. In here as S3. 0.5. In here on this side. S4. Here S5. On this side S6. Usually, the gap element will be modeled on the hardest point. Now, it should be modeled on the hardest point. On the lunge truss. No, on the lunge truss. And then I will add a gap element. So, I'll go to member. Add. Select this joint 1 and this. I will put the group as gap. No, gap. 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 Apply. Select this joint from here to here. Apply. 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 Now, what will be your fixity? Loadout is only resting. So, your fix should be Z axis. So, go to joint. Modify. And then select. Multiple selection of joint at the bottom. This one. Control. This one. This one. This one. Bottom. Bottom. Okay? Fixity is release. Release. XY. Fix. Z1. 0, 0, 1. 0, 0, 0. Apply. So it will look like that. You have to check here. I don't have member yet. So member, add from here to here. So you add gap. Save. Okay? So you have already now. So if you go to joint, details, modify, you select, it should have 001, 0001. Okay. Now, go to property, member group. We will define the gap, the gap element. Actually, this gap element is dummy. It means it doesn't exist. This is only to simulate no load or deflection. That's why you put this dummy. Define. Go to assume that this is tubular. 90 diameter. Assuming a wall thickness of 2.54 and yield stress of 24.8. And density, set this to 0.01. Small density will do. 0.01. Okay? Press OK. Close the model and save. Now you notice the support only is vertical. SACS will not run. It will be unstable. So you have to put it's either a spring support or 1-1. No? Fixity of 1-1. 0-0-0. So I will use spring. So go to joint. Go to springs. And then add spring here. Here. No? In here. In here. Add a jacket. Add a jacket. Add a jacket. On this side. On that side. This one. This one. This one. This one. On this one. And this one. So I will put apply. And then put X 100. Or you can put 10. I will just put 100. And then 100 also on Y. Do not put in Z. Press OK. So, save the file. And if I go to join, and details modify, you will see it's automatic. It becomes fixity of 1-1. Fixity of 1-1. Okay. In every gap element, you have to check if it's in compression. This is now compression. This gap element will not carry tension because it's just resting like this. Okay, this is my support. When it is shifted, this one will do like this, but it will not carry tension because it's just resting like this. When it's support, it should not follow like that. Because it's just resting. So it should be compression gap. Go to member. Go to details modify. Select this member, the gap. Press Ctrl for multiple selection. Select gap, 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 gap. Okay? The gap, the gap. And then scroll down. You should put member type compression. Compression, compression in this case. Press apply. What else? We need load combination. We will define in model. Okay. So, save the model, close this one, and go to data gen. Usually, I will perform load combination in the data gen because I just copy, paste, copy, paste. I will close this, and then I will go to data file. Select and drag. Okay. Now, scroll down. You delete some loadings, like SQ. We will delete this. SQW1. Delete SQW2. Delete this load combination SQ1. We don't need SQ. SQ only will be used during lifting. Delete. Delete. We don't need LFT1, right? We don't need that one. This is now the gravity load. Okay? This is gravity load. This is without COG shift. Okay? So the load gravity is weight of the structure plus the miscellaneous items. Okay? So GRB. So move up. Yeah? Remember this gravity load, This GRB, GRB. Okay? Move up. And then in here, load select. You should use the GRB. Delete left, left. Because your load is only gravity. Press OK. And take note, it should be gap. Gap, And then in the LDOP options, in here, double click the LDOP, this one. LDOP option. always check combine loads to basic option. Oh, check this one. Combine loads to basic option, meaning to say the combination will be converted into one loading, one load condition. Press OK and save. Just double click and then combine. See this one. Check this one. Combine loads to basic options.
This is just very fast. Right?
Check this. Combine loads to basic options, and you should consider gap. Okay? Okay? Press OK. Save the model. So that's the first step. Model the gap. Make it compress only. And change the load select into gap. And then you should check combine. Combine. Close the file. And we will make now the gap input. Now you notice the gap element are all in compression. But since we don't have the basis of design, we will consider no loads. Okay? I have actually here the figure. I forgot where I put it. So we will simulate this effect. This one, we will simulate this effect. Okay? For example, this is now the case. This is the barge. This is the barge. So winching force is applied here. So this jacket will move on that direction. So when this is the case, so assuming this support, this is on the K, supported by this, and this on the barge. This will be the case. How about if the barge is too low? It will look like that. So no support on the barge. So we will simulate that one. So this one, in this case, the limitation is not more than 100. So we will check. This support stub here will not carry any loading. So we will simulate no load on this. Right? No load. Okay, another case is like this. There is a load on the barge, and if you pull this, and it will look like this. Whoops. So this stub here has no load, right? So we will simulate that one, no load on gap. But the maximum deflection should not be more than 100. So that's our basis only. Now how about it's more than 100? What you will do? You will tell T&I contractor, please do not exceed this. So you have to consider the ballast tank plan at hand. Otherwise, your stress will be high. You cannot afford to have deflection more than 1,000. What will happen to the jacket? No, it's impossible. So we will simulate this effect. Okay? I will add input gap. So modeling, go to model. Modeling, modeling. Go to data gen. because in gap input is in datagen, not in preset. Preset is graphical, no? Datagen, create new data file, press OK, and then in static, go to static, select static, gap element, select gap element. Static, select gap element. Okay? Ready now? Select gap element and then press select. All gap elements in the model, you put yes. If you put yes, it will be like this, Just put yes. Maximum iteration will make this 9999, 9099. It should be in metric with newtons as force. I check yes, because all the element is in compression, and then we will override. We will make it no load. So press next. Override gap type for specific load case of any groups. This is not a group. We will consider member. No. Override gap type for specific load cases on any member. Just press yes. We will check. Yes, this one. Gap type override by member. So we will override the member. When you say you can make it no load. Okay. So I will put load case ID. Let us say GRB1. Just put GRB1. We will update this later on. And the element type is no load. You remember, we will simulate the no load. No load, The first member, we will go back to the file. So just put 1. Just put S1. S1. And then first member end, just put X, just like that. We will update this later on. Okay, and then press next. Override any more gap types. We don't need that one because we have already the LC gap. Press next. That's the end. That's the end. And then press save. Save the model. Save. And then put at the bottom. You put gap 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 input, and then delete the asterisk sign. Gap input, you can put that. You put jacket. Gap input jacket. Press save. Okay. So the file now is gap input jacket. Save. We will define gap GRB1 in the model, and then select what is that joint or member so that it will carry no load. Okay? Go to SACS model file. Go to model. Go to model. Okay. For example, I don't want this member to carry load. How to simulate for this member only, this one? So, it's like this. Support, 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 and this one without support. You can do this, You can do like this. I don't need gap elements. So, what will you do to simulate no load? I will remove the support here and then run a static analysis. That's the same with that. But if you will do like that, you have so many models. Like for example, I will delete this one. I will run analysis. Second, I will delete this one and put support here. I will delete this support here and then run analysis. That's 2. How about in here? That's 3. How about in here? That's 4. So too many files. While I can do only one model and then I will consider gap option. Okay. So for example, During loadout, no, it will move on that direction, assuming this member will not carry load. This one, So how to simulate no load on this member? So you have to select this member, and then check what is the detail for this S3101L. This member, I will consider no load on this member. So this is S3101L. Go to your file. This one. Your load is GRB. Double click. Your load is GRB. You remember GRB is our load condition, right? And then S3. And then 101L. Follow? See, this member is 3101L. So, I will assume that when this load is gravity GRB, no load on S3 101L. So, that's what it means. No load. On 101L. Press OK. And save. So, GRB include no load member S301 101L. And then perform gap element analysis. Okay. We'll check. We have the gap input and then run the analysis. Run the file wizard. Receipt. Receipt first. So you have now on the linear static analysis with gap element under jacket loadout folder. Start wizard. SACS input file. All files. Select that file. You have already that file, right? The model file. Press open. And use gap input file, of course. Select gap input jacket. Open. Select post view. Do not consider first the join check. We will check first if it's okay, working. So create post view. It's already done. Press OK. And then run the analysis. Okay, no errors. Go to post view. Go to post view. You have already. Post view. Okay. Try to notice what will happen. Display. Shape. Maximum displacement. 200. Maximum displacement. Check animation of shape. 200. Oh. So, there is no support on here. So that will happen in your jacket if no load on that or no support. What is the difference when you perform it in linear and you remove the support? It's the same. This is the unattached. It's unattached. Find hook one, find hook one. Oh, in here. You have to delete that one. Hmm? Skid. Cradle. Just the same. Just the same. We cannot model the cradle. So, like for example, skidway. Jacket. And then you have the saddle. This is the jacket. Now, we didn't model the saddle. We will not model the saddle. So, what you will do? If this is now your jacket and this is your support, all you have to do not model that and then consider only at the jacket hard points. Jacket hard points. I have a sample here. It's from so this one. This is the Bindong project. See? The support is on the hard points on the lance truss. So that's how to simulate. Because it's more conservative when your support is at the hardest point. Usually, can effect or can collapse will be critical on that. So that's because we cannot afford to join along the length of the skid. So you have to model the support on the hardest point. Here, 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 and here, and here. It's working already? You have, no, it's actually evaluation of the jacket. Yes, you have to evaluate also deflection. Like for example, this one, see? Deflection, display, labeling. You have to check the displacement. See, displacement here is 22 mm. It's okay. It's okay. So, without that support, still it's okay. Still your jacket is okay. So, you have to check punching. You have to check collapse on support. This is can collapse. And then member UC and punching. Miscellaneous check model. S3 is S3 is disconnected. Join. Fine. S3. Oh, in here. Oh, it's not fixed, Oh, why you put 111? 001. 001.
001.
Yeah. Play. At the bottom also everything. All. Control. Okay. That's wrong.
Yes.
Okay. Next, we will simulate the other side. Now we will simulate other side. How about when the other side has no load? What I mean is here, in here. So in this case, alternate, because this is what will happen. The center of gravity is here, the center of gravity is here of the jacket. If you remove this one, this supports, what will happen? Have you figured it out? The center of gravity is here. If no load in these two supports, what will happen to the jacket? It will be unstable. Why? Say the center of gravity is here. You remove the load here. The only support is this. And this one will be automatically cancelled by the program because this is compression. So, if you will put no load here and no load here, it will be unstable. At the same time, it will be not realistic. Why? When you skid it one, there's already a barge. Unlike you remove the barge and then you skid. So that's impossible. So we'll consider only support deflection here or no load here and no load on the other side. So how to simulate? I will select this. S6 and 181. No load on S6 and 181. So go to gap input. Okay? The first case is GRB, no load on S3 101L. And then the next case, no load on S6 181L. So I will go here, enter, and then just copy this one. Put the cursor here, right click, copy, put the cursor here, right click, and paste. Just only copy and paste. And then I will change the load combination because each combination has a different load case. I will put the combination GRB1. GRB1. And this one should be S6 and then 181L. Gravity 1 is 6, 181L. Okay? Press OK. And take note, we have already put a space. So cut that space. It should be continuous. GRB1, no load on member is 6181L. So save. Close this. And then make a load. Make a new load combination on the model. And then selection. Close this one. Close this one. I will go to the system input file, data file. Click here and then go to data file. Go to data file. I will select gap. Gap in here. The first one is GRB, the second one is, so double click, GRB1. GRB1. The first is GRB, the second is GRB1. Press OK. And you have your GRB1 also in the load combination. You should define that one. Scroll down. Now after this one, you add GRB1 in the load selection gap. GRB1 selection gap. Okay? After GRB1, scroll down and create another load combination. Right click, put the cursor here, right click, copy, put the cursor here, and the end, right click, and then paste. And then my new will be GRB1. GRB1. Okay? So that's my new load combination GRB1. Press OK. And then perform the analysis. So, we simulate that no load will occur on S6181L. The first on the side, the other one on the side. Okay? I will run analysis now. Run. Okay. And then go to post view. Say, go to display. Go to shape, maximum displacement, check animation shape, and make this 200 to make it slower. I will check dash. Na, for the deflected shape, dash. Press OK. So the first is GRB, right? GRB deflect in here. I want to deflect on this side. So I will go to load. Display. Next load. Okay, so it deflects now on this side. Oh. So that will happen on your jacket when no load on that side. On S6. The riser is not good to look at, na? You delete the riser, display, select plates, and then exclude riser, RS tab, and R is R. Riser tab. And then display, shape, so you can check punching. You can check punching. Have you performed joint can? Join. Review. In here, we will check what happened. 0.358. It's okay. Remember, UC is not more than 1, so this is okay in punching. Deflection is 14.98, so it's not more than 100. It's okay. Okay. So we will finish at Thursday. We will consider here, here, and then no load here, and then combine. No load here, and then combine. So the most case scenario, no? The worst case again. Basic. Just basic. Okay? So there will be a quiz. Maybe Thursday, I don't know, Thursday, it depends on the schedule, Thursday or Friday. We will just give you the model, the geometry, and then you perform. And then if you have some questions, you can ask. I will go one by one. So that's much better. Rather than... Okay, so thank you. See you tomorrow.
Yes.
You don't drink beer? No. Huh? So you in
Tomorrow.
next day? Yeah. No, in the office. Okay, thank you, gentlemen. Lady also.